This video is about logarithms. In maths, every function has its reverse. Addition has subtraction, multiplication has division, and even trigonometric functions have their inverses. If we have a way of getting somewhere, we have a way of getting back. This is the case with exponents, or powers. You may be thinking the answer is square or cube roots, and so on. Well, there's actually another different function that's considered to be the reverse of exponentials, and that is called a logarithm. It does look a little confusing when written out, but the gist of it is this. The first number, the little one, is called the base. The next number is the number that we're taking the logarithm of. You'll hear it referred to as log to the base 2 of 8, for example. Then we have the answer, which is what the log is equal to. In this case, it's a nice simple number, 3, but it won't always be, which is why we often leave things in logarithm form, as we have certain laws that we can use to simplify them in other ways. Seeing these both written out, you'll be able to see the connection between them. The base is the same in both scenarios, but the variable of the logarithm corresponds to the answer of the exponential, and the power of the exponential corresponds to the answer of the logarithm. Essentially, when using logs, we are saying what power do I need to put a to get b. So what power do I need to put 2 to get 8? The answer is 3, because 2 to the power of 3 is 8. This is different to how we use roots, as with roots we're saying what number to the power of a will give me b. So what number to the power of 3 will give me 8? The answer is 2, because 2 to the power of 3 is 8. We can summarize this in a way. If we use the exponent shown here, then we can see that the exponent uses x and y to find z, the logarithm uses x and z to find y, and the root uses y and z to find x. This is handy if you're given one of these and you need to find the other. In practice, you won't really ever have to do any roots more complicated than square or cube, but if you do, you can express them as powers. This actually shows part of the reason why logarithms are the actual inverse of exponents rather than roots. Roots can be expressed as powers, while logarithms cannot. There's a special log function for log to the base e. If you watch the exponential video, then you'll know that e is often given to the power of something. So if we have a number, we can find what number e was given to the power of. Log to the base e is called log natural and is represented by ln. You may also see log written without a base. Don't panic too much, this just means log to the base 10, as old calculators could only use log to the base 10. This also explains why changing base is on the curriculum. You used to have to change base into base 10 to work with logarithms. I'll get to changing logs soon, but first I need to cover something so that we can move on to laws of logarithms. What happens if we have log to the base x of x? Well, based on what we know about logarithms, this is saying what power do I need to put x to get x? The answer should fairly obviously be 1, as x to the power of 1 is x. But a slight variation on this is log to the base x of x to the k. So what power do I have to put x to get x to the power of k? The answer is k, because x to the power of k is x to the power of k. This is important to remember. Now, laws of logarithms. These are the 3 laws of logarithms. I'm going to go through them now, but you can read through them yourself, or you can skip this section if you're just not interested. So, let's set x to be equal to a to the power of p, and y to be equal to a to the power of q. This means that log to the base a of x is equal to p, and log to the base a of y is equal to q. So, if we do x times y, this is equal to a to the power of p plus q, because of the laws of indices. So if we have a to the power of p times by a to the power of q, we get a to the power of p plus q. If we take log to the base a of xy, then this is the same as taking log to the base a of a to the power of p plus q. Using the law that I stated on the previous slide, this comes out to be the same as p plus q, as this is the k in our scenario. Now, because p is equal to log to the base a of x, and q is equal to log to the base a of y, then p plus q is equal to log to the base a of x plus log to the base a of y. And as this is all equal to log to the base a of xy, log to the base a of xy is equal to log to the base a of x plus log to the base a of y. If we do the same thing here, setting x to be equal to the power of a to the power of p, and y to be equal to a to the power of q, we can then say that x divided by y is a to the power of p divided by a to the power of q, and is therefore equal to a to the power of p minus q using laws of indices. Then log to the base a of x over y is the same as log to the base a of a to the power of p minus q, which simplifies to p minus q. P is equal to log to the base a of x, q is equal to log to the base a of y, so log to the base a of x over y is equal to log to the base a of x minus log to the base a of y. Now, the last one is slightly different. We only need x in this scenario, which is again set to a to the power of p. So log to the base a of x is p. If we set x to the power of k, this is the same as setting a to the power of p to the power of k, which using laws of indices will simplify to a to the power of pk. If we then set log to the base a of x to the k, we can then see that this is the same as setting log to the base a of a to the power of pk, and is therefore equal to pk. And because p is log to the base a of x, and k is a constant, and so we leave it, that means that log to the base a of x to the k is equal to k times log to the base a of x. Now, time for a bonus law of logarithms, which is changing logs. This is how logarithms used to be worked out on old calculators. But essentially, what we have is this on the left is our original expression that we will be given, which is that log to the base a of x is equal to log to the base b of x over log to the base b of a. So in old calculations, you would put b equal to 10, and then you would put, say, if you wanted to find log to the base 2 of 8, you would put log to the base 10 of 8 over log to the base 10 of 2. You don't need to worry about this too much. It probably won't come up on a question, and you don't need to know it because your calculator will be able to do logarithms just fine. As long as you remember these and how indices work, such as negative and fractional indices, then you should be fine for logarithms. As long as you remember all of these things, then you should be able to answer any question with ease. Thanks for watching.